Look up at the night sky. What do you see? A scattering of distant stars, maybe a planet or two, the faint glow of the Milky Way stretching across the darkness. But beyond what our eyes can perceive, hidden in the vast cosmic ocean, something extraordinary is happening. Some of the most massive stars in the universe, hypergiants, are sending out signals we can't explain. Not just one or two, but dozens of mysterious pulses, flickers, and echoes that defy everything we think we know about how stars behave. These aren't just random blips in the data. They're deliberate, structured, and utterly baffling. And today, we're going to dive deep into 25 of the most perplexing signals ever detected, each one a cosmic riddle waiting to be solved. Imagine a star so colossal it makes our sun look like a speck of dust. Hypergiants are the titans of the cosmos, burning brighter and dying faster than any other stars. But their sheer size isn't the only thing that makes them strange. These celestial behemoths are whispering secrets, sending out bursts of energy, rhythmic pulses, and even what some scientists describe as stellar heartbeats that follow patterns we can't decipher. Are these natural phenomena, or could they be something more? Some researchers have dared to ask, could these signals be intentional? The possibility alone sends shivers down the spine. This isn't just about astronomy, it's about unlocking one of the greatest mysteries of our time. Every unexplained signal is a piece of a puzzle that could rewrite the textbooks. Some seem to repeat at precise intervals like cosmic lighthouses. Others vanish as suddenly as they appear, leaving astronomers scrambling for answers. And then there are the ones that shouldn't exist at all, defying the laws of physics as we know them. Together, we'll explore these enigmas, from the eerie ghost pulses of VY Canis Majoris to the bizarre frequency shifts of RW Cephei. By the end, you'll see the night sky differently, not just as a static backdrop, but as a living, breathing entity full of questions we've only just begun to ask. So, are you ready to listen to what the stars are trying to tell us? Let's begin. One of the most mesmerizing signals comes from a star so volatile, it could rewrite our understanding of stellar behavior, Eta Carinae. This hypergiant isn't just massive, it's practically a cosmic force of nature, with eruptions so powerful they briefly outshone our entire Milky Way in the 19th century. But what really captivates astronomers isn't just its explosive past, it's the strange, pulsing radio emissions it sends out like a malfunctioning beacon. Unlike the steady rhythms of pulsars or the predictable flares of smaller stars, Eta Carinae signals are chaotic, surging and fading without warning. Picture a lighthouse flickering erratically, its beam cutting through the fog in no discernible pattern. That's what telescopes detect from this star: radio waves that spike and plummet in ways our models can't explain. Some pulses last for hours, others vanish in minutes, and here's the kicker: these emissions don't match the star's visible light activity. Normally, a star's radio signals correlate with its brightness, but Eta Carinae operates on its own rules. It's as if there's a hidden engine beneath its fiery surface, generating these radio bursts independently. What makes this even stranger is the nebula surrounding Eta Carinae, a vast, twisted cloud of gas and dust ejected during its historic eruptions. This nebula should absorb or distort radio waves, yet the signals cut through cleanly, almost as if they're being focused or amplified by some unseen structure. Compare that to a smaller star like Betelgeuse, whose radio emissions are muffled by its own stellar wind, and the anomaly becomes even more glaring. Could this be evidence of magnetic fields warping in ways we've never observed? Or is there something buried in Eta Carinae's core, a dense companion star perhaps, that's driving these erratic transmissions? The theories are as wild as the star itself, but one thing's certain: Eta Carinae isn't just defying expectations, it's taunting us, daring scientists to crack its code. And with every unexplained pulse, it reminds us that the universe still holds mysteries too big for our textbooks. VY Canis Majoris doesn't just break records, it shatters them. This hypergiant is so colossal, if placed at the center of our solar system, its surface would reach past Saturn's orbit. Yet despite its staggering size, the most intriguing thing about this star isn't its sheer scale. It's the faint, whispering radio signals that ripple outward like cryptic messages. Unlike the violent eruptions of Eta Carinae, these emissions are subtle, almost delicate, as if the star is murmuring secrets just beneath the threshold of our hearing. Tuning into these whispers isn't easy. VY Canis Majoris is shrouded in thick clouds of dust and gas, remnants of its own violent outbursts over millennia. Normally, such dense material should smother radio waves, turning them into indecipherable static. But instead, astronomers detect something unexpected: structured pulses, weak but unmistakably rhythmic. It's like trying to overhear a conversation through a thunderstorm, and catching a few clear, deliberate words. So what's causing these signals? One leading theory points to magnetic fields woven into the star's atmosphere, far more complex than anything we've seen before. Picture a tangled web of invisible threads, vibrating as the star's turbulent surface churns beneath them. These magnetic filaments could act like cosmic antennas, converting the star's chaotic energy into those eerie, coherent waves. But there's a problem. Our current models can't fully explain how fields of that strength could form around a hypergiant. Then there's the interstellar interference angle. Some researchers suggest these whispers might not originate from the star at all. Instead, they could be echoes, radio waves from distant galaxies or even long-dead stars, bent and amplified as they pass through VY Canis Majoris's dusty envelope. It's the celestial equivalent of a funhouse mirror, distorting signals from across the cosmos into something that looks like it's coming from the star itself. But here's what keeps scientists up at night. A handful of these signals repeat at intervals that don't match any known natural process. Too steady to be random turbulence, too irregular to be a pulsar's clockwork beat. Could there be structures, vast, unknown features hidden in the star's swirling depths? Or is this the fingerprint of something even more extraordinary, a phenomenon we haven't yet imagined? Every whisper from VY Canis Majoris pulls us deeper into the mystery, proving that sometimes the quietest voices in the universe hold the loudest questions. Betelgeuse has always been a star that demands attention, not just because of its fiery red glow in Orion's shoulder, but because it behaves like a temperamental giant, flaring, dimming, and keeping astronomers on their toes. But in late 2019, something unprecedented happened. The star didn't just dim visibly, it fell eerily silent in the radio spectrum weeks before its dramatic light drop. That silence was more unsettling than any outburst. It was as if the universe hit a mute button on one of its loudest voices, and scientists are still scrambling to understand why. Radio waves from massive stars like Betelgeuse usually come from their chaotic outer layers, where superheated gas and magnetic fields churn like a storm. These emissions aren't steady, they fluctuate with the star's activity, much like static from a distant thunderstorm. But in the months leading up to Betelgeuse's great dimming, that static vanished. Telescopes tuned to its frequency picked up nothing. No crackles, no surges, just an unnatural hush. For a star that's typically a cosmic chatterbox, this quiet was deafening. Some researchers argue this radio silence was a warning sign, a precursor to the massive ejection of material that later obscured Betelgeuse's light. Imagine a volcano going quiet before it erupts, the calm before the storm. If that's the case, the star wasn't just dimming. It was reorganizing itself internally, maybe even preparing for a future supernova. But here's the twist: when Betelgeuse finally did dim, its radio emissions didn't return right away. Instead, they stayed muted for months, as if the star's outer layers had been fundamentally altered. Others propose a stranger explanation. What if the radio shutdown wasn't about the star's activity at all, but its magnetic field? Betelgeuse's magnetism is a labyrinth of forces we barely understand. If those fields suddenly collapsed or reconfigured, they could have stifled the radio waves entirely, like a power grid going offline. There's even a fringe theory that the star's interior convection, the roiling currents that drive its energy, hit a temporary standstill, effectively putting its radio voice box on pause. Then there's the supernova question. Betelgeuse is a prime candidate to go supernova in our cosmic neighborhood, possibly within the next 100,000 years. Could this radio silence have been a rehearsal for that final act? Supernova precursors are poorly understood, but some models suggest stars might undergo strange, quiet phases before collapsing. If so, Betelgeuse's silence wasn't just a hiccup, it was a glimpse into the final stages of stellar life. What's certain is that Betelgeuse didn't follow the script. Most dying stars ramp up their activity before major eruptions, not shut down. This deviation hints at gaps in our understanding of hypergiants, gaps wide enough to drive a supernova through. Every time we think we've figured Betelgeuse out, it throws another curveball, reminding us that the universe's most massive stars play by their own rules. And that's what makes its sudden silence so haunting, not just because it was unexpected, but because it's a mystery we still haven't solved. HR 5171A isn't your average hypergiant, it's a cosmic oddity even among titans. This binary star system, where one hypergiant orbits another massive companion, has been caught emitting something astronomers have never seen before: rhythmic, repeating bursts of radio energy. Not random spikes or chaotic flares, but precise, clockwork pulses that arrive like cosmic metronome ticks. What makes these bursts so baffling isn't just their regularity, it's that they defy every known mechanism for how binary stars interact. Picture two stars locked in a gravitational dance, each with stellar winds so powerful they could strip atmospheres off nearby planets. When these winds collide, they typically create chaotic shockwaves, a messy, turbulent frontier where energy dissipates in all directions. Yet HR 5171A's bursts are anything but messy. They're clean, sharp, and arrive like clockwork every 8 months. It's as if something in this system is funneling all that chaotic energy into a focused beam, turning a stellar wrecking ball into a precision laser. One leading theory points to the hypergiant's hidden companion. We know it's there. Its gravity tugs on the primary star, altering its shape into a teardrop, but could it also be acting like a cosmic conductor? Some models suggest the companion's magnetic field might be orchestrating these bursts, channeling colliding winds into periodic eruptions. Think of it like squeezing a balloon until it pops. As material builds up at a choke point between the two stars, the pressure finally releases in a coordinated burst. Except in this case, the pop happens on a schedule with a precision that feels almost engineered. Then there's the shadow of a third object. A handful of astronomers speculate that an unseen planet or brown dwarf might lurk in this system, its gravity subtly tuning the timing of these bursts like an unseen hand adjusting a dial. It's a long shot. Planets around hypergiants are theoretically unstable, but if confirmed, it would rewrite our understanding of how extreme star systems form. But the most tantalizing clue lies in the bursts themselves. Unlike pulsars, whose radio pulses are generated by rapid spin, HR 5171A's rhythm is tied to its orbital motion. Each burst arrives just as the stars reach a specific point in their dance, suggesting the phenomenon is rooted in their intricate gravitational interplay. Yet even this explanation leaves gaps. If the bursts are purely mechanical, why do some cycles produce stronger signals than others? And why do occasional missed beats appear in the data, as if the system occasionally forgets to fire? Every 8 months, like a celestial alarm, HR 5171A reminds us that the universe still holds patterns we can't yet decrypt. Whether it's magnetic symphonies, hidden worlds, or something entirely new, one thing is clear. this binary hypergiant isn't just breaking the rules. It's writing its own. NML Cygni isn't just another hypergiant, it's a cosmic kaleidoscope, bending light and twisting signals in ways that leave astronomers utterly perplexed. This star, one of the largest known in our galaxy, emits radio waves with a bizarre property. They're intensely polarized, as if passing through some invisible cosmic filter. Normally, radio waves from stars scatter in all directions, like sunlight glinting off rippling water. But NML Cygni's signals come out orderly, aligned in specific orientations that suggest something extraordinary is happening in its chaotic depths. Picture trying to push a tangled slinky through a narrow tube. The coils resist, bending and warping under pressure. That's the kind of struggle happening around NML Cygni, where its monstrous stellar winds collide with dense clouds of dust and molecules in its envelope. This turbulent environment should randomize any polarization, yet the signals emerge with striking consistency. It's as if the star's outer layers contain hidden structures, perhaps colossal magnetic fields, twisted into bizarre configurations by the star's rotation. Or worse, our understanding of plasma physics might be missing a crucial piece. One clue lies in the asymmetry of NML Cygni's envelope. Unlike the neat, spherical shells around smaller stars, this hypergiant's outer layers are lopsided, stretched and distorted like taffy pulled from one side. Animations based on radio observations reveal vast plumes of gas arcing away from the star, as if something, maybe an unseen companion or an explosive eruption, kicked the system off balance centuries ago. These irregularities could act like cosmic lenses, selectively filtering certain polarizations while scattering others. Then there's the temperature paradox. Polarized radio waves often come from extremely hot or cold environments where particles align in strong magnetic fields. But NML Cygni's envelope is a weird middle ground, too warm for some polarization mechanisms, yet too cool for others. Some researchers speculate that microscopic dust grains spinning in sync with magnetic fields might be responsible. Others propose that shockwaves rippling through the envelope are generating temporary, orderly zones amid the chaos. The most tantalizing possibility, NML Cygni might be harboring a magnetic monster at its core. Hypergiants aren't supposed to sustain highly structured fields due to their turbulent interiors, but if this star's sheer size has allowed a stable magnetic dynamo to form, it could be sculpting those polarized signals like a potter shaping clay. If true, it would force us to rethink how magnetic fields behave in the universe's most extreme environments. Every polarized pulse from NML Cygni feels like a cipher, a coded message from a realm where the rules of physics bend under the weight of sheer stellar might. Whether it's magnetic labyrinths, rogue shockwaves, or something entirely unseen, one thing's clear. This hypergiant isn't just breaking the mold, it's melting it down and recasting it into shapes we've never imagined. RW Cephei stands out even among hypergiants, not for its size alone, but for the two bizarre signals it emits in concert, like a star playing a dissonant cosmic duet with itself. The first anomaly comes in the form of violent X-ray flares erupting unpredictably from its seething surface. For a star of its class, these eruptions shouldn't happen at all. X-rays typically originate from stars with strong magnetic activity, but RW Cephei's turbulent outer layers should suppress such structured outbursts. Yet here they are, sharp, high-energy spikes punching through the noise, defying every model of stellar behavior. The flares follow no discernible pattern. Some last mere minutes, others smolder for days. Even stranger, they don't always coincide with visible changes in the star's brightness. Normally, a hypergiant's X-ray activity mirrors its optical flares like a thunderclap following lightning. But RW Cephei's X-rays arrive without warning, as if something deep within its broiling atmosphere is cracking open periodically, releasing pent-up energy like steam through a fissure. One theory suggests these outbursts might stem from magnetic reconnection, a process where tangled magnetic fields suddenly snap and realign, unleashing torrents of radiation. But hypergiants like RW Cephei aren't supposed to sustain stable magnetic fields long enough for such events. It's like finding a perfectly tuned violin in the middle of a hurricane. Then there's the second anomaly, rhythmic infrared oscillations pulsing gently beneath the chaos like a heartbeat muffled by layers of thick fabric. While X-rays reveal the star's fury, these infrared shifts expose its quieter, stranger side. Over weeks and months, the star's heat signature ebbs and flows in slow, almost meditative waves, far too regular to be random turbulence, yet too irregular to match known pulsation cycles. Imagine a candle flickering in a draft, except the flame dims and brightens on a schedule only it understands. What ties these two phenomena together is RW Cephei's unstable outer layers, a roiling, semi-detached atmosphere hanging precariously above its core. The star's immense gravity can barely hold onto this gaseous shroud, creating a region of extreme density shifts where material constantly teeters between falling back inward and escaping into space. This instability might explain both anomalies. The X-ray flares could be shock waves from collapsing pockets of gas, while the infrared oscillations may trace the slower, grander rhythm of the entire outer layer breathing in and out. But there's a twist. Some astronomers argue these signals aren't just side effects of instability, they could be clues to something deeper. Hypergiants like RW Cephei are thought to be on the verge of shedding their outer layers entirely before a supernova. If so, these erratic X-rays and infrared whispers might be the star's final act of self-destruction, played out in real time. Every unexplained flare, every mysterious pulse, could be a preview of the cosmic spectacle to come, a countdown we're only beginning to decode. WOH G64 doesn't just pulse, it breathes. Deep in the large Magellanic Cloud, this hypergiant emits radio waves with a rhythm so steady, it's been nicknamed the stellar heartbeat. Unlike pulsars, which flash with the precision of atomic clocks, WOH G64's pulses are slower, more organic, rising and fading like the chest of a sleeping giant. Every 400 days, like clockwork, its signal strengthens and weakens in a cycle that mirrors the ebb and flow of a living thing. But here's the catch: stars this massive aren't supposed to have heartbeats. Pulsars owe their regularity to rapid spin, their lighthouse beams sweeping across space as they rotate. WOH G64, by contrast, is too bloated and unstable to spin that way. Instead, astronomers suspect its pulses stem from something far stranger, gargantuan waves rippling through its outer layers. Picture a pot of water on the verge of boiling the surface shutters as heat rises from below. Now scale that up to a star over 1,500 times wider than our Sun, with convection currents so vast they could swallow solar systems whole. These oscillations, known as stratonational waves, might be compressing and expanding the star's atmosphere like a colossal bellows, generating those rhythmic radio whispers. But even this explanation raises new questions. For one, the signal's clarity defies expectations. Hypergiants are notoriously messy, their surfaces racked by eruptions that should scramble any coherent pattern. Yet WOH G64's heartbeat cuts through the noise with eerie consistency, suggesting something is stabilizing these oscillations. One radical theory points to an invisible scaffold of magnetic fields woven through the star's outer layers like a cosmic spiderweb. These fields could channel the chaos into orderly pulses, turning turbulence into music. Then there's the matter of timing. 400 days is an oddly specific interval, too long for typical stellar pulsations, too short for orbital cycles. Some researchers wonder if the star's heartbeat is a symptom of something deeper, perhaps material sloshing in an off-kilter core, or even the ghostly influence of a distant companion star tugging at its rhythms like a moon pulling tides. Others speculate this could be a preview of the star's death throes, a prelude to the moment when its core finally buckles under its own weight. WOH G64's heartbeat isn't just a curiosity, it's a challenge. Every pulse forces us to reconsider what we know about hypergiants, these tempestuous titans that refuse to follow the rules. Whether it's hidden magnetism, seismic stellar waves, or something even more profound, one thing is clear: this star isn't just alive. It's speaking to us, and if we listen closely, it might just teach us a new language. IRC plus 10,420 doesn't just flare, it haunts. This hypergiant, shrouded in its own expelled gas like a phantom wrapped in tattered robes, has astronomers chasing echoes from its past. Years after violent outbursts, when the star's visible light has long faded, something bizarre happens. Delayed radio signals emerge as if the star is whispering secrets from beyond its own timeline. It's not a glitch in the data. These aren't random blips. They're precise, ghostly repetitions of earlier eruptions, replaying like cosmic vinyl records scratched by time itself. The key lies in the star's circumstellar envelope, a vast, intricate maze of dust and gas ejected during its tempestuous life. Ordinarily, light and radio waves zip through such material in seconds. But IRC plus 10,420 envelope is so dense, so labyrinthine, that photons get lost in the chaos. Picture a flashlight beam bouncing through a hall of mirrors, each reflection fainter than the last. Now imagine that hall is light years wide, with walls of molecular gas thick enough to trap radiation for years before reluctantly letting it escape. That's the delay mechanism at work here, light playing an interstellar game of hide and seek. Spectral analysis reveals even stranger details. When scientists compare the original outbursts to their delayed echoes, the signals aren't identical. Certain frequencies are amplified, others vanish entirely. It's as if the circumstellar material isn't just slowing the light, it's filtering it, reshaping the signal like a cosmic equalizer. Some wavelengths scatter against dust grains, while specific molecules like silicon monoxide absorb and re-emit others, creating spectral fingerprints that weren't present in the original flare. This isn't passive reflection, it's an active transformation, with the envelope acting as both prison and alchemist for the star's radiation. Then there's the shape of the echoes. Most delayed signals from cosmic objects like supernova spread outward in predictable, spherical shells. But IRC plus 10,420 echoes arrive in jagged, asymmetrical waves, hinting at an envelope twisted by magnetic fields or sculpted by unseen companions. Recent radio interferometry maps show vast spiral structures within the gas, possibly caused by a binary partner's gravitational pull that could funnel light along preferential paths. If true, it means the echoes we detect aren't just random reverberations. They're messages distorted by the star's own architecture, cosmic breadcrumbs scattered through a maze only partially visible to us. The most unsettling possibility: some of these echoes don't match any recorded outburst. Either we missed the original events, unlikely given modern monitoring, or IRC plus 10,420 envelope is so efficient at trapping light that signals from centuries ago are still looping inside, occasionally leaking out like half-remembered dreams. If that's the case, every echo we catch might be a fragment of the star's history, a piece of its past refusing to fade. And that raises a chilling question. How many other hypergiants are whispering to us from their own forgotten moments, their oldest cries only now reaching our telescopes? U-Antli performed the ultimate cosmic disappearing act in 2015, vanishing from the radio spectrum so abruptly it left astronomers rubbing their telescopes in disbelief. One moment, this hypergiant was broadcasting its usual chaotic symphony of emissions. The next, silence, not a gradual fade, not a flicker, just an off switch flipped somewhere in the void. For 3 long months, every instrument pointed at U-Antli heard nothing but empty static, as if the star had been temporarily erased from existence. What makes this dropout so unsettling isn't just its suddenness, but the fact that Antley's visible light barely wavered. While other stars dim when shrouded by dust or plasma, this one kept shining steadily, its luminosity unaffected even as its radio voice went mute. It's like watching a singer mouth words onstage while their microphone cuts out. The performance continues, but the signal doesn't reach the audience. The leading explanation, a freak magnetic storm in the star's outer layers, powerful enough to scramble radio emissions without disrupting the light we see. Picture a solar flare so intense it creates a temporary dead zone around the star, a bubble of distorted magnetism that absorbs or deflects radio waves before they can escape. Yet there's a rival theory, an immense fast-moving dust cloud. Hypergiants like Antley are notorious for coughing up colossal quantities of soot-like carbon particles which can clump together unexpectedly. If one of these dense formations passed between the star and Earth at just the right angle, it might have selectively blocked radio frequencies while letting visible light slip through. The problem: dust clouds usually leave spectral fingerprints, specific infrared glows from warming particles, and Antley's dropout came without those telltale signs. The mystery deepens when you compare it to other radio-silent stars. Take VY Canis Majoris, which faded gradually over years as its expelled material built up a natural radio shield. Or Betelgeuse, whose quiet moments often precede visible dimming. Antley fits neither pattern. Its dropout was too clean, too sudden, and too isolated to align with known stellar behavior. Even more bizarre, when the star's radio emissions finally returned, they did so at full strength. No recovery period, no lingering weakness. Some researchers wonder if we witnessed a rare stellar glitch, a momentary reconfiguration of Antley's outer layers that temporarily altered how it generates radio waves. Others speculate about unseen companion objects, like a rogue planet or neutron star, whose gravity might have stirred the hypergiant's atmosphere into an opaque knot. But perhaps the most intriguing possibility is that Antley's vanishing act was neither accident nor anomaly, but a routine phase for hypergiants we've simply never caught before. After all, stars this massive live fast and die young, their life cycles packed with violent transitions we've barely begun to catalogue. Whatever the cause, Antley's silence speaks volumes. In a universe where stars are supposed to fade predictably, this hypergiant rewrote the script and left us with a puzzle that refuses to dissolve into the background noise of space. Rho Cassiopeiae doesn't just dim its screams. This yellow hypergiant, one of the rarest and most unstable stars in our galaxy, has a habit of plunging its surface temperature by thousands of degrees without warning. But what really stuns astronomers isn't the sudden cooling, it's the deafening radio shrieks that erupt during these events. Ultra-high frequency spikes, far beyond the usual stellar static, pierce through the cosmic background like a siren in the dark. These aren't gradual shifts in emission, they're violent, abrupt, and unlike anything else observed in stellar physics. Think of a glass shattering in slow motion, except instead of glass, it's the outer layers of a star millions of times larger than Earth. Rho Cassiopeiae's temperature drops aren't gentle transitions. They're catastrophic collapses where the star's bloated atmosphere contracts violently, triggering shock waves that ripple outward at supersonic speeds. The resulting radio spikes could be the sound of those shock waves slamming into surrounding gas, like cosmic thunderclaps echoing across light years. But here's what defies explanation. The frequencies detected are too high, too clean, to match standard models of stellar turbulence. It's the difference between hearing a distant storm and suddenly picking up a razor-sharp scream amid the wind. One theory suggests these screams stem from explosive mass loss, a phenomenon where Rho Cassiopeiae doesn't just shed material steadily, but in violent, episodic eruptions. Imagine a volcano spewing ash, except instead of rock, its entire solar masses of superheated gas blasted into space. As these ejected layers collide with older debris, the impacts might generate those piercing radio signals. Yet even this explanation falls short. Spectroscopic data reveals something unnerving. The star's outer layers aren't just cooling during these events. They're fragmenting like a pane of glass riddled with cracks just before it implodes. What if the screams aren't just side effects but symptoms of something deeper? Rho Cassiopeiae belongs to a class of stars teetering on the edge of instability, where the balance between radiation pressure and gravity is so precarious that even minor fluctuations can cascade into full-blown stellar tantrums. Some researchers speculate that these radio spikes are evidence of failed supernova, moments when the star almost tears itself apart, only to pull back from the brink at the last second. The screams, then, might be the sound of a star fighting for survival, its outer layers rebelling against the crushing weight of its own core, the most haunting detail. Rho Cassiopeiae's outbursts aren't random. They cluster in cycles, with decades of eerie quiet punctuated by frenzied periods of activity. It's as if the star is holding its breath, building toward something inevitable. Every scream feels like a warning, a reminder that even the mightiest stars are fragile, and that the universe has voices we're only beginning to hear. VY Cephei is supposed to be the textbook example of a binary star system, two massive stars locked in a gravitational embrace, each influencing the other's behavior. Yet when astronomers tune their instruments to this hypergiant, they hear something impossible. A signal so smooth and unified, it's as if the companion star doesn't exist. No duet of conflicting rhythms, no telltale Doppler shifts from orbital motion, just a single, flawless emission, like a cosmic ventriloquist throwing its voice across light years. The paradox deepens when you examine the system's dynamics. VY Cephei's companion, a blue supergiant, orbits so close that its stellar wind should be constantly battering the hypergiant's outer layers, stirring up turbulence that would fracture any coherent signal. Instead, the radio waves arrive pristine, as if filtered through some unseen cosmic sieve. One explanation is as unsettling as it is elegant. The companion might not just be orbiting VY Cephei, it could be siphoning off its emissions like a thief in the night. Imagine two singers standing side by side, one belting out a powerful note while the other silently mouths the words. In stellar terms, the blue supergiant's intense ultraviolet radiation might be ionizing the hypergiant's outer atmosphere, stripping away electrons and transforming it into a natural amplifier. This ionized shell could act like a radio lens, bending and focusing VY Cephei's emissions into a beam so narrow that the companion's contributions vanish into the background. It's the celestial equivalent of a spotlight so bright it drowns out everything else on stage. But there's a wilder possibility lurking in the data. Recent simulations suggest the companion's gravity might be warping space-time around the hypergiant, creating a subtle gravitational lens that distorts the signals en route to Earth. Picture a funhouse mirror that doesn't just bend light, it smooths out imperfections, turning a chaotic chorus into a single, pure tone. If true, this would mean we're not hearing VY Cephei as it truly is, but as its companion's gravity wants us to hear it. The most tantalizing clue lies in the signal's stability. Binary systems typically produce fluctuations as their stars eclipse or disrupt each other's winds. Yet VY Cephei's emissions remain eerily steady, almost as if something is actively correcting for these disturbances. Some theorists speculate about magnetic bridges, invisible filaments of force connecting the two stars, channeling energy so efficiently that the system behaves as one. Others wonder if we're witnessing a new class of stellar symbiosis, where two stars don't just orbit but merge their identities in ways we've never seen. Whatever the answer, VY Cephei's binary paradox forces us to rethink the boundaries between stars. In a universe where even the most colossal objects can hide their true nature, this hypergiant reminds us that sometimes the deepest mysteries don't come from the void between stars but from the spaces where they collide. S Persei operates in shadows. While most hypergiants announce their tantrums with dazzling light shows, this star prefers stealth, emitting bizarre, dark radio bursts that arrive without any optical fanfare. Telescopes catch the spikes clear as day, but point any visible light instrument at the same patch of sky during these events, and you'll find nothing. No flares, no dimming, just radio waves screaming into the void from what appears to be an otherwise unremarkable star. It's as if S Persei has a hidden compartment, a secret chamber where physics operates by different rules. These bursts share eerie similarities with one of the universe's most elusive phenomena, failed supernova. When massive stars collapse inward without the telltale explosion, they're theorized to emit neutrino pulses so powerful they could ionize surrounding gas, generating radio static without visible light. The math almost fits. S Persei's bursts pack enough energy to match a stellar core's death throes. But there's a glaring hole in this theory. Failed supernova should be one-time events, while S Persei's dark pulses recur every few months like clockwork. Either we're witnessing a star dying in slow motion, imploding piece by piece, or something entirely unrelated is at work. Primordial black holes offer another tantalizing explanation. These hypothetical relics from the Big Bang, no larger than asteroids but as massive as moons, could be orbiting S Persei like invisible wolves circling a fire. Each time one passes through the star's outer layers, its immense gravity might compress surrounding plasma just enough to spark radio emissions before vanishing again without optical traces. The timing would be random, but modern simulations show these ancient black holes could get trapped in gravitational dances around massive stars, creating semi-regular disruption patterns. Yet the strangest clue lies in the burst structure. Unlike the chaotic static of plasma turbulence, S Persei's pulses often split into clean double peaks, a signature usually seen when fast-moving objects interact with magnetic fields. Some astronomers suggest we might be detecting a dense, compact body, perhaps a neutron star or white dwarf carving through the hypergiant's magnetosphere like a ship through fog. The lack of X-rays makes this unlikely, but not impossible. S Persei's thick atmosphere could be muffling higher energy emissions while letting radio waves slip through. What chills researchers most is the lingering question of scale. If these dark pulses truly represent new physics, whether crumbling stellar cores, primordial black holes, or something even stranger, they might be happening everywhere, hidden in plain sight. S Persei could be the first we've noticed simply because its sheer size amplifies the signals. That realization turns every quiet patch of sky into a potential frontier, whispering that the universe's greatest shows might not be the bright ones, but the shadows moving just beyond the spotlight. VY Cygni doesn't broadcast, it stutters. This hypergiant's radio emissions arrive in clusters so oddly timed, they've sparked heated debates among astronomers. Not the steady pulses of a dying pulsar or the erratic bursts of a turbulent star, but something unsettlingly in between. Erratic yet rhythmic, like a cosmic Morse code operator with a broken transmitter. The pattern defies natural explanations without quite crossing into the realm of artificial. It's this eerie middle ground that keeps researchers staring at their screens long after midnight, wondering if they're witnessing stellar physics or something beyond. At the heart of the mystery are VY Cygni's triplet bursts, groups of 3 rapid-fire radio spikes separated by inconsistent pauses. Sometimes the gaps last minutes, other times hours. Yet when analyzed statistically, these pauses aren't entirely random. They cluster around certain intervals, creating a faint but detectable rhythm beneath the chaos. It's as if the star is trying to follow a rulebook written in invisible ink, its transmissions slipping in and out of coherence. The closest natural analog comes from magnetars, neutron stars with crust-quaking starquakes that emit radio bursts. But VY Cygni isn't a dense remnant, it's a bloated leviathan whose sheer size should prevent such precise vibrations. The controversy ignites when you map the burst structure. Advanced signal processing reveals subtle repetitions, certain spike sequences reappearing months or even years apart, like refrains in a discordant song. While natural processes can produce repeating patterns, these particular sequences exhibit a statistical fingerprint more complex than typical stellar noise. Some researchers argue the structure could arise from resonant cavities in the star's atmosphere, regions where magnetic fields trap and amplify radio waves, releasing them in fragmented echoes. Others point to the hypergiant's hypothetical debris disk. If VY Cygni hosts ancient rings of planetary wreckage, passing fragments might trigger periodic disruptions in its magnetic field. Then there's the fringe hypothesis, the one that makes SETI researchers lean forward despite their skepticism. A small but vocal group suggests the patterns resemble what engineers call forbidden codes, signal structures so inefficient for natural processes that they're statistically unlikely to emerge spontaneously. On Earth, we use similar encodings for error correction in noisy channels. Of course, Occam's razor favors mundane explanations over alien Morse code. But VY Cygni's transmissions linger in that uncomfortable gap where natural phenomena start to look intentional. The truth may lie in the star's turbulent heart. Hypergiants like VY Cygni often pulsate as their cores wrestle against gravity, creating pressure waves that ripple outward. Normally, these vibrations are too chaotic to produce clean signals. But if VY Cygni's interior happens to resonate at specific frequencies, like a cathedral amplifying certain musical notes, those vibrations might structure its radio emissions into quasi-patterns. Supporting this, spectrographs show faint hints of matching oscillations in the star's visible light, as if its entire bulk is humming in discordant harmony. For now, VY Cygni keeps its secrets. Each new burst feels like a cipher with half the pages missing, too structured to dismiss as noise, too messy to declare a message. Whether it's magneto-hydrodynamic symphonies, cosmic debris playing percussion, or something even stranger, one thing's clear: this hypergiant isn't just breaking the rules of stellar communication. It's rewriting them in real time, one enigmatic triplet at a time. HD 179821 doesn't just flicker, it conjures ghosts. This hypergiant, cloaked in the veil of its own expanding nebula, has astronomers questioning their instruments every time its so-called phantom jet materializes. Unlike the blazing, relentless beams shooting from quasars, powered by voracious supermassive black holes, this jet appears and vanishes like a mirage, leaving no trace behind. One moment, radio telescopes detect a narrow, high-energy stream stretching light years into space. The next, it dissolves into the cosmic background as if it were never there. The strangest part, this jet shouldn't exist at all. Hypergiants like HD 179821 lack the compact, spinning cores needed to launch such focused outbursts. Quasars achieve their iconic jets through the extreme physics of their accretion disks, matter spiraling into black holes at nearly light speed, twisted into beams by magnetic fields billions of times stronger than Earth. But HD 179821 is a turbulent, loosely bound monster, its energy diffused across a surface so vast it could engulf Jupiter's orbit. For it to produce a jet would be like a bonfire spontaneously firing a laser beam. The leading theory suggests we're not seeing a true jet at all, but a cosmic sleight of hand, gravitational lensing. Picture a massive object, perhaps a rogue planet, a dim brown dwarf, or even a cluster of dark matter, drifting between the hypergiant and Earth. As its gravity bends the star's radio emissions, it could momentarily focus them into a faux jet, a trick of space-time as fleeting as a desert mirage. Supporting this, the phantom jet's spectral signature doesn't quite match typical high-velocity plasma. Instead, it carries faint hints of smearing, wavelengths stretched and compressed as if strained through an invisible colander. Yet there's a wrinkle. Lensing effects usually distort light symmetrically, creating arcs or rings like Einstein's famous cross. this jet appears razor straight, defying the warped geometry we'd expect. Some astronomers propose an exotic solution, a parabolic lens, where the intervening object isn't just massive but moving at tremendous speed, its gravity carving a temporary tunnel through spacetime. Others wonder if HD 179821's own nebula is to blame, its dense, lopsided shells of expelled gas acting as a natural radio waveguide, channeling emissions into brief, coherent bursts. Then there's the outlier possibility that we're glimpsing something entirely new. Hypergiants in their death throes are known to shed material in violent pulses. Could the phantom jet be the aftermath of one such eruption, a collapsing bubble of magnetized plasma briefly focusing radio waves like a dying star's farewell signal? Or perhaps evidence of a hidden neutron star companion, its influence occasionally piercing the hypergiant's chaos to launch a temporary streak across the cosmos. Every time the phantom jet vanishes, it leaves behind more questions than answers. Is it a trick of the light, a structural oddity, or a phenomenon we've yet to name? For now, HD 179821 keeps its secrets, flickering between reality and illusion like a star that refuses to be fully seen. WOH Cephei and VY Sagittarii, two crimson titans burning at the ragged edge of stellar existence, should be chaos incarnate. Yet these red hypergiants emit signals so peculiar they've earned the nickname the Enigma pair. Take WOH Cephei first. Its radio emissions don't pulse or flare like other massive stars. They sing. Not metaphorically, actual harmonic frequencies ripple through its output, layered like chords in some cosmic choir. The dominant tone, a deep, resonant hum at 0.007 Hz, a vibration so low it would take 2 full minutes to complete a single cycle. For comparison, the lowest note on a grand piano vibrates at 27.5 cycles per second. WOH Cephei's song is a bass rumble beyond human hearing, resonating across light years like the slow, steady breath of a sleeping god. What could cause such a phenomenon? One compelling theory points to substellar vibrations, waves rippling through the star's unfathomably dense core, where pressures crush atoms into exotic quantum soups. Picture dropping a pebble into a tar pit. The surface barely moves, but deep below, slow motion ripples propagate. Now replace the tar with degenerate matter, a state so dense a teaspoon weighs more than a mountain, and you're close to imagining WOH Cephei's inner workings. These vibrations might travel upward, warping the star's magnetic field like fingers plucking a colossal harp string, converting mechanical energy into radio harmonies. Yet even this explanation stumbles. Substellar waves should dampen quickly in hypergiants, their energy dissipating in the turbulent outer layers. WOH Cephei's song remains pure, its harmonics uncorrupted, as if something's tuning the star from within. Then there's VY Sagittarii, WOH's silent counterpart. This hypergiant emits virtually no radio noise at all, except for one baffling exception: sporadic gamma-ray whispers, so faint they flirt with the limits of detection. Gamma rays typically scream from the universe's most violent events: supernova, neutron star collisions, black hole jets. For a single star to produce them quietly, like someone clearing their throat in a library, defies all expectations. The whispers arrive in clusters, each lasting microseconds, packing the energy of a solar flare into bursts narrower than a lightning strike. Stranger still, they coincide with VY Sagittarii's thermal pulses, moments when the star's helium-burning shell reignites, sending shockwaves through its atmosphere. Normally, this should trigger X-rays, not gamma. One radical hypothesis suggests these rays might be Cherenkov radiation, not from water, as in nuclear reactors, but from particles tearing through the star's own atmosphere faster than light can travel there. It's like catching the sonic boom of a jet, except the jet is made of protons and the air is a hypergiant's roiling outer layers, but the true shocker. VX Sagittarii's whispers are polarized, their electric fields aligned in ways that suggest an ultra-strong magnetic funnel somewhere near the star's core. That shouldn't happen in red hypergiants. Their interiors are too turbulent to sustain organized fields, unless, of course, we're wrong about what lurks inside. Some models now speculate that VX Sagittarii's core might be spinning much faster than its surface, creating a dynamo effect normally seen in neutron stars. If true, this hypergiant isn't just dying. It's hiding a cosmic matryoshka doll, a stellar corpse already forming deep within its fiery shroud. Together, WOH Cephei's song and VX Sagittarii's whispers paint a portrait of extremes, one star vibrating like a struck bell, the other firing gamma-ray Morse code from the void. They remind us that the universe's most massive objects often speak in riddles, their signals carrying secrets we're only beginning to decode. And sometimes the quietest voices, the hums and whispers, hold the loudest truths. Westerlund 126 isn't just a hypergiant, it's a cosmic time traveler. Or at least its signals behave like they're stuck in some celestial traffic jam, arriving years behind schedule compared to every astrophysical model. Imagine shouting into a canyon and hearing your echo a full minute later, except this canyon is light years wide, and the delay defies everything we know about how sound, or in this case, light, should travel through space. The anomaly first caught astronomers' attention when they noticed something peculiar about the star's radio pulses. These emissions, which should have taken roughly 16,000 years to reach Earth based on Westerlund 126's distance, arrived with a bizarre hiccup. Certain frequencies lagged behind others by measurable margins, as if space itself had been stretched thin along the path. It's not just a uniform delay either. High-frequency waves, which usually outpace their lower counterparts in interstellar space, show up later than expected, a complete inversion of normal dispersion. Redshift measurements deepen the mystery. When light traverses expanding space, its wavelengths stretch, shifting toward the red end of the spectrum. Westerlund 126's light exhibits this shift, but with strange kinks in the data. Specific spectral lines, fingerprints of elements like hydrogen and helium, are redshifted more severely than others, as if they've passed through pockets of exaggerated spacetime curvature. The effect resembles light passing through a funhouse mirror, but instead of glass, the distortions stem from something far more profound: gravity warping the fabric of the universe itself near the star. One explanation points to Westerlund 126's unimaginable gravitational influence. Hypergiants this massive don't just bend spacetime, they twist it into knots. If the star's immediate surroundings contain regions of extreme curvature, think of a bowling ball resting on a trampoline, but with space itself as the fabric, light taking different paths through this warped zone could arrive at wildly different times. Supporting this, recent simulations suggest the star's colossal mass might have created a temporary gravity well in its vicinity, a dip in spacetime so steep that signals struggle to climb out. But there's a twist. If gravity alone were responsible, the delays should correlate neatly with the star's activity cycles. Instead, the lapses seem to cluster unpredictably, like a faulty cosmic elevator that stops at random floors. Some theorists speculate about unseen mass hidden near the star, perhaps a dormant black hole or a knot of dark matter, creating additional gravitational lensing. Others wonder if we're seeing evidence of tired light, a controversial idea where photons lose energy over vast distances, not from cosmic expansion, but through some undiscovered interaction with the quantum vacuum. The most tantalizing possibility: Westerlund 126 might be sitting at the center of a primordial spacetime wrinkle, a relic from the early universe where space never fully smoothed out. Picture a blanket that's been folded for so long the creases resist flattening. If such structures exist, they'd act like speed bumps for light, selectively slowing certain wavelengths while letting others pass undisturbed. It's a radical notion, but one that would explain why this hypergiant signal seemed to wander through time before finally reaching us. Every delayed pulse from Westerlund 126 forces us to reconsider the shape of space itself. Not just as an empty stage where stars perform, but as a dynamic, malleable fabric, one that might still bear the scars of creation, hidden in plain sight until a hypergiant's light exposes them. V766 Centauri doesn't just shine, it crackles. Known as the diamond star for its carbon-rich atmosphere, this hypergiant emits a relentless barrage of static, like a cosmic radio drowning in interference. Unlike the crisp pulses of neutron stars or the rhythmic flares of younger, hotter stars, V766 Centauri's noise is chaotic, unstructured, and oddly reminiscent of an electrical storm, except scaled up to stellar proportions. The question isn't just what causes this static, but how a star's chemistry could turn its entire atmosphere into a celestial short-wave radio nightmare. At the heart of the mystery is the star's composition. Most hypergiants are dominated by hydrogen and helium, their atmospheres too thin and hot for complex chemistry. But V766 Centauri is a carbon monster, its outer layers teeming with sooty molecules like cyanide and carbon monoxide. Under the right conditions, these compounds can ionize, shedding electrons that turn the atmosphere into a conductive plasma soup. The result, a natural circuit board the size of a solar system, where turbulent winds and magnetic fields might generate discharges powerful enough to distort radio emissions across light years. Picture a thunderstorm where lightning strikes aren't fleeting bolts but continent-sized arcs, sustained for days or even weeks. Then there's the static's peculiar structure. Close analysis reveals not pure noise, but something closer to bursty turbulence, sudden surges of signal riding atop a steady hiss. These spikes resemble terrestrial interference from electrical grids, where overloaded transformers spit out jagged radio waves. On Earth, such noise stems from electrons jumping gaps in faulty wiring. On V766 Centauri, the gaps might be literal. Fractures in the star's own magnetosphere, where magnetic field lines snap and reconnect, unleashing cascades of charged particles. Supporting this, spectrographs show traces of highly ionized carbon, a signature of extreme voltages ripping electrons from their atoms. The wildest theory, though, involves diamond itself. Lab experiments show that under immense pressure, carbon crystals can become piezoelectric, generating electricity when flexed by sound waves or vibrations. V766 Centauri's interior churns with convection currents powerful enough to slosh entire oceans of molten carbon. If even a fraction of this material crystallizes into diamond-like structures near the surface, their piezoelectric properties could be amplifying the star's natural vibrations into radio static. It's a stretch, but then again, so is the idea of a star made of diamond in the first place. Yet the static might not originate from the star alone. V766 Centauri's extended atmosphere is so thick with carbon dust that it acts like a celestial Faraday cage, trapping and re-radiating electromagnetic noise from deeper within. Some astronomers argue we're hearing echoes radio waves bouncing endlessly between layers of soot until they escape by chance, their original coherence scrambled into white noise. Others suggest the dust itself is the culprit, its grains rubbing together like socks on carpet, building up electrostatic charges that discharge in crackling stellar-scale sparks. Whatever the cause, V766 Centauri's static is more than just cosmic background fuzz. It's a fingerprint of chemistry pushed to extremes, a reminder that even the most familiar elements can behave unpredictably under stellar pressures. And if carbon-rich hypergiants truly can generate electrical storms, it opens a chilling possibility. Elsewhere in the universe, a diamond star might not just crackle, it could scream. RSGC1 F01 doesn't just emit radio waves, it casts shadows with them. This hypergiant, lurking in the star cluster RSGC1, sends out pulses that twist and contort as if something massive but utterly invisible is tugging at them. The signals don't drift or scatter randomly, they shift in precise, repeating arcs, tracing the outline of an unseen orbit. It's like watching a marionette dance when you can't see the strings or the puppeteer. What makes this shadow so unsettling is its consistency. Every 97 days, the hypergiant's radio emissions warp in the same peculiar pattern, as if responding to an invisible companion's gravitational pull. Normally, such behavior would point to a binary partner, but telescopes find nothing. No star, no debris disk, not even a wisp of dust where the object should be. The math is clear. Something with at least 12 times the mass of Jupiter is circling RSGC1 F01, yanking its plasma into these telltale shapes, yet the sky there remains stubbornly, eerily empty. One possibility sends chills down the spines of astrophysicists: a free-floating black hole. These rogue relics of dead stars, stripped of their accretion disks and visible only through their gravitational fingerprints, could orbit unseen, warping spacetime so severely that even radio waves bend around them. If one were skating through RSGC1 F01's outer atmosphere, its gravity might sculpt the hypergiant's emissions into those regular distortions. Supporting this, the signal's warping matches simulations of a compact object moving at nearly 200 kilometers per second, a speed typical of black holes kicked into motion by ancient supernova kicks. But there's a rival explanation buried in the data. Dark matter, the universe's most elusive substance, is thought to clump around massive objects like hypergiants. Could RSGC1 F01 be tangled in a dense knot of it? These hypothetical dark matter halos wouldn't emit light, but their gravity could still tug on the star's plasma, imprinting those periodic signal shifts. The challenge: we've never directly detected dark matter's gravitational effects on this scale. If RSGC1 F01's shadow confirms its presence, it would be a first, a ghostly hand finally leaving fingerprints. Then there's the wild card, a primordial black hole, forged not from a dying star but in the chaos of the Big Bang itself. These ancient anomalies, some no larger than a grapefruit but as massive as a planet, could lurk throughout the galaxy. One passing near RSGC1 F01 might explain the signals without requiring a bound orbit. Like a ship creating brief ripples in a pond, it could distort the hypergiant's emissions as it drifts by. The catch: primordial black holes remain theoretical, but finding one would rewrite cosmic history. The most haunting detail: RSGC1 F01's shadow doesn't decay. Over a decade of observations, the pattern hasn't weakened or wandered, as you'd expect from a passing object. Whatever's out there is locked in a stable dance with the hypergiant, an invisible partner in a ballet we can only hear through distorted radio whispers. Until we glimpse the unseen dancer directly, this signal stands as a cosmic riddle, a reminder that the universe's darkest secrets often hide in plain sight, revealed only by the light they bend. St. 218 doesn't just erupt, it warns us first. This hypergiant's most baffling quirk isn't the violence of its outbursts, but the eerie fact that its radio signals arrive before the visible fireworks begin. It's like hearing thunder before seeing lightning, a reversal of cause and effect that seems to defy cosmic logic. But the truth behind this reverse shockwave phenomenon isn't faster than light trickery. It's a masterclass in how energy navigates the brutal physics of a dying star. Picture a tsunami forming far offshore. The first sign isn't the wall of water itself, but the sudden pull of the tide as the ocean recoils. St. 218 operates on a similar principle, just scaled up to stellar proportions. When instability brews in its core, the initial energy release doesn't blast outward as light. Instead, it triggers shock waves that plow through the star's dense inner layers like a bulldozer through wet cement. These collisions generate low-frequency radio waves which slip through the star's atmosphere relatively unimpeded. Visible light, however, gets trapped in the traffic jam of superheated plasma, only escaping once the shockwave finally reaches the surface and erupts into space. What makes this sequence so counterintuitive is the timescale. For most stars, light and radio emissions are nearly simultaneous, but hypergiants like St. 218 are so vast, their interiors so layered and opaque that signals take wildly different paths. Radio waves, being less prone to scattering, act like seismic sensors, transmitting the star's internal tremors almost instantly. Light, meanwhile, plays a brutal game of pinball, absorbed and re-emitted countless times before breaking free. The result, a celestial false alarm where the echo arrives before the shout. The real twist lies in the shockwaves themselves. Simulations reveal these aren't simple pressure fronts, but fractal splinters of energy that branch and merge as they climb through the star's gravity well. Some fragments even ricochet backward, creating interference patterns that further delay the visible outburst. It's this chaotic journey that stretches milliseconds into days, turning stellar physics into a cosmic magic trick where the reveal precedes the setup. Yet the most profound implication isn't about St. 218 alone. It's a window into how we observe the universe. If hypergiants can scramble the sequence of their own demise, what other cosmic events might we be misreading? Supernova, gamma-ray bursts, even black hole formations could harbor similar temporal illusions, their true timelines hidden beneath layers of stellar sleight of hand. Every preemptive radio pulse from St. 218 is a reminder. In the cosmos, what we see isn't always what's happening, it's just what finally made it out of the chaos. The Pistol Star doesn't just shine, it hums. This hypergiant, one of the most luminous stars in our galaxy, emits radio waves with an uncanny precision, twin frequencies locked in perfect harmony, like a cosmic tuning fork struck against the void. Most stars broadcast a cacophony of chaotic noise, but the Pistol Star's signals are eerily clean, oscillating between two distinct pitches with the regularity of a metronome. It's as if the universe itself is using this star to play a duet, and we're just beginning to catch the melody. At the heart of this phenomenon lies the star's photosphere, the roiling, ultra-dense layer where light finally escapes into space. Normally, this region churns with turbulence, its plasma bubbling like water in a boiling pot. But the Pistol Star's outer layers seem to vibrate in sync, creating resonant harmonics that amplify certain frequencies while suppressing others. Picture blowing across the top of a glass bottle. The pitch you hear depends on the cavity's size and the air's vibration. Now scale that up to a star 25 million times more luminous than our Sun, its entire atmosphere ringing like a colossal bell. The twin frequencies could be the natural harmonics of this stellar resonance, a byproduct of the star's sheer size and the strange physics of its ultra-hot plasma. Yet there's another possibility lurking in the data, an unseen companion. Binary stars often generate rhythmic signals as they orbit, their gravitational dances stirring up periodic vibrations. The Pistol Star's twin frequencies might trace the footsteps of a hidden partner, a neutron star or even a smaller black hole, tugging on the hypergiant's atmosphere like a puppeteer pulling strings. Supporting this, the frequency ratio matches what you'd expect from two massive objects locked in a tight, resonant orbit. Each time the companion swings close, its gravity could compress the hypergiant's photosphere, triggering a pulse at one frequency, while the rebound as it pulls away generates the second. The wildest part, these frequencies aren't static. Over decades of observations, they've drifted slightly but detectably, as if the tuning fork is being bent by some immense force. One explanation points to the Pistol Star's extreme mass loss. It's shedding solar masses worth of material every few centuries, like an iceberg crumbling into the sea. As its outer layers evaporate, the photosphere's resonant properties shift, altering the pitch of its cosmic hum. Another theory suggests the companion's orbit is decaying, spiraling inward as gravitational waves bleed energy from the system. If true, the star's song could one day fade entirely, swallowed by the silence of a merger, but the most tantalizing clue lies in the harmonics themselves. When astronomers convert the frequencies to sound waves, they form a near-perfect musical fifth, an interval so harmonious it's foundational to nearly every earthly musical tradition. Coincidence, perhaps, but it's a reminder that the same physics governing violins and flutes might also sculpt the radio whispers of hypergiants. The pistol star isn't just a marvel of astrophysics, it's a bridge between the cosmic and the artistic, a reminder that the universe's grandest phenomena often resonate in ways that feel strangely, beautifully familiar. G67 doesn't just radiate, it inhales and exhales. This hypergiant, anchored near the chaotic heart of our galaxy, pulses with a rhythm so precise it mimics the rise and fall of a sleeping giant's chest. Every few decades, its radio emissions surge as an immense shell of plasma expands outward, only to contract again in a slow, cosmic sigh. Unlike the violent eruptions of other massive stars, these movements are eerily smooth, as if the star itself is breathing in time with some unseen celestial metronome. The key to this phenomenon lies in thermal instability, a delicate balance between radiation pressure and gravity that most hypergiants can't sustain. Picture a balloon half filled with water held over a flame. The heat makes the air inside expand, but the water's weight keeps it from bursting. G67 operates on a similar principle, its outer layers caught in a tug of war between the star's fierce radiation pushing outward and its own crushing gravity pulling inward. When radiation gains the upper hand, the atmosphere billows outward, emitting a strengthening radio whisper. As gravity reasserts control, the shell collapses back, dimming the signal like a slow fade on a cosmic radio dial. What sets this hypergiant apart is the regularity of its cycle. Most unstable stars flare unpredictably, their outer layers shedding material in chaotic spasms. But G67's breaths follow a 60-year cadence with near-clockwork precision, a timescale so long it spans generations of astronomers. The star's radio shells aren't just expanding and contracting, they're doing so in perfect thermodynamic sync, like the piston of a perfectly tuned engine. Spectroscopic analysis reveals why, unlike younger hypergiants whose outer layers churn with turbulence, G67's atmosphere has settled into distinct, stable zones. It's the difference between a boiling pot and a simmering one, both hot, but one controlled enough to cook with. The real surprise came when researchers mapped the shells in 3 dimensions. Instead of the expected spherical bubbles, the radio waves traced twisted, spiral-shaped structures, as if the star's breath were spinning as it expanded. This helical pattern hints at something profound. G67 isn't just breathing, it's breathing in a magnetic whirlwind. The hypergiant's rotation, combined with colossal magnetic fields woven through its plasma, might be sculpting these spirals, turning what should be simple expansions into cosmic corkscrews. Yet the most haunting question remains: what happens when the breathing stops? Hypergiants like G67 are living on borrowed time, their cores fusing elements at a breakneck pace. Some models suggest these rhythmic pulses could be the star's final act of stability before its outer layers detonate in a supernova. Others argue the breaths might actually prolong its life, regulating mass loss like a safety valve on a pressure cooker. Either way, each radio sigh from G67 feels like a countdown, a reminder that even the most majestic cosmic rhythms are fleeting, their echoes fading into the silence of deep space. S. Doradus burns with the fury of a star that refuses to play by the rules. A hypergiant so luminous it blurs the line between star and supernova. But buried within its searing 20,000-degree inferno lies something that shouldn't exist: a cold spot. Not just a minor temperature dip, but a chilling anomaly that defies the very physics of stellar interiors. While the rest of the star rages like a blast furnace, this region emits radio waves as if it were a cosmic air conditioner had been switched on in the middle of a wildfire. At the heart of the mystery is the cold spot's sheer improbability. Hypergiants like S. Doradus are meant to be thermal maelstroms, their energy distributed evenly by convection currents powerful enough to drag entire oceans of plasma from core to surface. Yet radio maps reveal a stubbornly cool patch spanning thousands of kilometers, its emissions muted like a whisper in a thunderstorm. The temperature gradient is so sharp it's less like a star and more like a flashlight beam hitting a frosty window, light and dark coexisting where they should have long since cancelled each other out. One explanation points to relics of the star's violent past. S. Doradus is a known variable, prone to eruptions that eject shells of material into space. Could this cold spot be the shadow of an ancient magnetic field, frozen into place when one of those eruptions backfired? Picture a tornado suddenly flash frozen mid-rotation, its structure preserved but its energy trapped. In stellar terms, a magnetic loop might have snapped during an outburst, leaving behind a dead zone where charged particles can no longer heat the plasma efficiently. Supporting this, the cold spot's edges show faint polarization, a telltale sign of magnetic influence clinging to the wreckage of a once active field. Then there's the accretion disk fragment theory. Hypergiants aren't supposed to harbor disks, those belong to newborn stars or black holes. But if S. Doradus once cannibalized a companion star or rogue planet, the debris could have formed a temporary ring of cooler material. Most of it would have vaporized instantly in the star's heat, but a dense fragment might have survived long enough to sink into the photosphere, where it now floats like an iceberg in a sea of lava. Radio spectrographs show traces of heavy elements in the spot's emissions, metals like iron and silicon that typically sink inward, not linger near the surface. But the most unsettling possibility, the cold spot isn't a relic at all. It's something alive. Recent simulations suggest hypergiants might develop bizarre plasma structures called stratonuclei, self-sustaining eddies where turbulence and magnetism conspire to create temporary order amid chaos. Think of a whirlpool that refuses to dissipate, its currents reinforcing its own walls. In S. Doradus's case, such a structure could act like a stellar-scale heat sink, siphoning thermal energy from its surroundings and radiating it away in frequencies we can't detect. If true, the cold spot isn't an accident, it's a phase of matter we've never catalogued, thriving in conditions we thought impossible. Every radio scan of S. Doradus deepens the riddle. The cold spot doesn't drift or fade like a dying ember. It persists anchored to the star's rotating frame as if bolted there by invisible hands. Whether it's magnetic archaeology, stellar cannibalism, or an entirely new form of plasma physics, one thing's clear: this hypergiant isn't just breaking the rules. It's rewriting them in real time and leaving us to decipher the edits. IRC plus 10,420 final act wasn't just a signal, it was a scream cut short. In 2022, this hypergiant emitted a radio burst so erratic it seemed to document its own unraveling in real time. For 17 hours, telescopes captured a rapid-fire sequence of pulses, each one quicker and more desperate than the last, like a dying star tapping out its last Morse code. Then, at the peak of the frenzy, silence, not a gradual fade, not a sputter, a hard stop, as if someone had yanked the cosmic plug. The pattern didn't just end, it was severed mid-cycle, leaving astronomers with a chilling question. Did we just witness the moment IRC plus 10,420 core gave up the fight? What makes this transmission so unnerving is its structure. Most stellar death throws follow predictable arcs, rising instability, a peak eruption, then decay. But IRC plus 10,420 finale played out like a glitching record, its pulses accelerating exponentially before the abrupt cutoff. Spectral analysis reveals why. The frequencies weren't just increasing, they were compressing, as if the star's internal vibrations were ratcheting toward some critical threshold. Picture a spring coiled too tight, vibrating faster and faster until it snaps. That's what the data suggests happened deep inside the hypergiant, a runaway collapse where the core's oscillations overwhelmed its ability to hold shape. The timing aligns eerily with supernova precursor models. When massive stars near death, their cores can undergo acoustic neutrino damping, a process where vibrations bleed energy into ghostly particles instead of sound. This drains stability, causing the core to shudder at frequencies radio telescopes can detect. IRC plus 10,420 final pulses match these predicted death rattles, right down to the sudden quiet that would follow a core's final collapse. Yet there's no visible explosion, at least not yet. Light travels slower than radio waves through a hypergiant's dense interior. If the core did implode, the shockwave might still be climbing toward the surface, meaning the supernova's light could reach us months or even years after the radio's last gasp. That's why telescopes worldwide now train on IRC plus 10,420 like sentinels waiting for a storm. Hypergiant supernovae are rare, perhaps once a century in our galaxy, and catching one in its earliest phases could rewrite stellar physics. The star's position helps. Nestled in the relatively sparse Cygnus region, any explosion would shine unobscured by interstellar dust, but the wait is agonizing. Every day without a visible outburst deepens the mystery. Was the 2022 signal truly a core collapse or some bizarre false alarm? The answer might lie in IRC plus 10,420 ghostly echoes. Even after its final transmission, delayed radio waves from older eruptions continue trickling in, bent by the star's labyrinthine dust envelope. Some of these echoes now show strange distortions, subtle warps that suggest the hypergiant structure is shifting in ways models can't yet explain. Whether these are death spasms or mere growing pains, one thing's certain: IRC plus 10,420 has entered uncharted territory. And when, not if its light finally reaches us, the universe will stage a spectacle unseen since Kepler's supernova in 1604. Until then, we watch, we listen, and we wonder if the silence itself is the most terrifying signal of all. These mysterious signals from hypergiant stars aren't just cosmic oddities. They're keys to unlocking some of the biggest unanswered questions in astrophysics. Each bizarre pulse, eerie whisper, and sudden silence forces us to reconsider what we thought we knew about how stars live, die, and interact with the fabric of space itself. Some patterns suggest hidden laws of physics waiting to be discovered, while others point to evolutionary stages we've never witnessed before. Take the rhythmic pulses of WOH G64 or the harmonic hum of WOH Cephei. These aren't random noise. They're systematic, almost deliberate, hinting at underlying processes far more structured than the chaotic interiors of hypergiants should allow. Are we seeing the fingerprints of magnetic fields behaving in ways our models can't yet predict, or evidence of hypergiants transitioning into entirely new phases of stellar existence? One of the most tantalizing possibilities is that these signals document the final acts of hypergiants before their inevitable collapse. Stars like IRC plus 10,420, with their delayed echoes and sudden radio silence, might be showing us the precursors to supernova in real time, something astronomers have never directly observed in such detail. If we can decode these patterns, we could predict which hypergiants are on the verge of explosion, giving us a front-row seat to one of the universe's most violent and transformative events. But there's a catch. Not all hypergiants follow the same script. The Pistol star's harmonic frequencies and S Doradus's inexplicable cold spot suggest that these stars might have multiple evolutionary paths, some leading to supernova, others to strange, unexplored ends. Then there's the wild card, entirely new physics. The time-warped signals from Westerlund 126 and the gravitational shadow circling RSGC1 F1 don't just challenge our understanding of stars, they poke holes in our models of spacetime itself. Could hypergiants, with their immense gravity and turbulent atmospheres, be creating localized distortions in the fabric of the cosmos. Some theorists speculate that these stars might be natural laboratories for extreme phenomena like quantum gravity effects or dark matter interactions, processes so subtle we'd never detect them anywhere else. The eerie precision of HR 5171A's bursts or the unnatural polarization of NML Cygni's radio waves might be glimpses of physics operating at scales or energies we've yet to imagine. Yet for every tantalizing pattern, there's an equally baffling exception. VY Canis's flawless radio emissions in a binary system, or St. 218's reverse shockwaves where radio arrives before visible light, refuse to fit neatly into any theoretical framework. These outliers might be the most valuable clues of all, revealing where our current models fall short. Are we missing a fundamental force that governs hypergiant behavior? Or is the truth even stranger? Could these stars be influenced by exotic, unseen companions, from primordial black holes to rogue planets with freakish orbits? The open questions are as vast as the stars themselves. How do hypergiants sustain coherent magnetic fields when their interiors should be turbulent beyond measure? Why do some, like Betelgeuse, fall radio silent before erupting, while others, like Antliae, vanish without warning? And perhaps the biggest mystery of all, are these signals random cosmic noise or the first whispers of a deeper stellar language we're only beginning to hear? Every unexplained burst, every ghostly echo, is a piece of a puzzle that could rewrite our understanding of the universe's most massive stars and the laws that govern them. Until then, these hypergiants remain both sphinxes and storytellers, guarding their secrets in plain sight. These towering, turbulent stars, these hypergiants screaming into the void, aren't just cosmic oddities. They're mirrors. Every unexplained signal, every pulse that defies our models, reflects something fundamental about our place in the universe. We are still learning to listen. For all our telescopes and supercomputers, we've barely scratched the surface of what these giants are trying to tell us. Each flicker from VY Canis Majoris, each harmonic hum from the Pistol Star, is a reminder that the cosmos operates on scales and rhythms we're only beginning to perceive. And isn't that astonishing, that after centuries of mapping the skies, the universe still holds voices we can't yet understand, whispers from the very edges of physical possibility? This isn't just astronomy, it's a testament to human curiosity. Long before we had radio telescopes, our ancestors looked up at Betelgeuse's fiery glow and wove stories about its meaning. Today, we chase those same questions with spectral analysis and magnetohydrodynamic simulations, yet the wonder remains unchanged. There's something profoundly humbling about realizing that a star like IRC plus 10,420 might have collapsed into a supernova years ago. Its light still traveling toward us, its final act playing out in slow motion across the void. We are always catching up, always piecing together the universe's secrets like detectives arriving late to the scene, and that's why these signals matter. Not just for the science, though unraveling them could rewrite textbooks, but for the way they ignite our collective imagination. When you hear the rhythmic heartbeat of WOH G64 or the eerie silence of Antliae, you're not just observing data. You're eavesdropping on a conversation billions of years in the making, one that predates our species and will outlast our civilizations. That's the magic of astronomy. It connects us to something vast and timeless, reminding us that the universe is far stranger, far more inventive than we could ever dream up alone. So stay curious. The next great cosmic revelation might be hiding in the static of V766 Centauri, or the polarized whispers of NML Cygni, waiting for someone to crack the code. And who knows, maybe your eyes scanning these words right now will be the ones to spot the pattern everyone else missed. Space is full of surprises, and the next chapter of this story belongs to all of us. If one of these signals gripped you, whether it's the binary paradox of VY Cephei or the diamond star's crackling storm, drop it in the comments. Let's keep the conversation as vibrant as the stars themselves. Don't forget to subscribe. The universe isn't done astonishing us, and neither are we. The cosmos is speaking. All we have to do is keep listening.